so this is our 310 notes on our march to getting done at 313. So we've only got, after this one, we've only got three more sets of notes to do. So we'll do 312, 311, 312 tomorrow, and then 313, I believe, is on. Well, your test is a little farther off because the next week you're working on Beer's Law Lab pretty much for 3 days straight, and then the last day you're working is a progress check discussion, and then when you come back from that 3-day break, then you have your test. Yeah. You have a test on Monday, Tuesday.
The day after Halloween.
Yeah, it's the 1st.
Wait, what's a 3-day break?
You have the 29th off. You have 3 days this week. Next week you have 4 days. That you go to school.
We have 4 days.
Oh,
we
go.
4 days this week.
Wait, we have 3 days this week.
No, you don't go to school on Thursday this week.
Yeah, so Thursday, Friday, Sunday, 4-day break.
4-day break. You go to school for 3 days this week. You go to school for 4 days next week.
Next week, we have Monday off or Friday.
Friday.
They should have made it Monday.
Thursday is the end of quarter, and so Friday is like it's a professional development day, but I'm guessing they were hoping to maybe put in some time in there this week. Great. All right, I'm going to start my notes now. If you'd like to join me, otherwise we are going to have some issues, guys. Here we go. All right, so solubility, and we will eventually get to the point in the later next semester where you will actually calculate which one of these things is more soluble than another. Okay, we haven't gotten there yet. We've got to introduce some other stuff and everything, but eventually we're going to do calculations and you'll be able to see, well, this one's way more soluble than that one. This one, very little of it is soluble, and you'll be able to put it kind of on a scale at that point, but we're not there yet. So solubility describes the extent to which solute will dissolve into solvent to form a solution. Typically that solvent is water, and if it is water, then we denote that behind our parts of our equation with the in parentheses and kind of subscript AQ. All right, like I said, water is the most common solvent here, and that's what makes it aqueous solution. So water is highly polar, and because of that, you're going to be able to pull apart these ionic compounds. So if we had like sodium chloride, for example, your water is going to come along. Okay, this is a positive ion. It's going to get attracted to the oxygen part of your water, and then your chlorine is going to get attracted to the hydrogen part of the water here because it's negative. And if the attraction to water is greater than the attraction between the ions, then it's going to be soluble. If that's not the case, if this is stronger, for example, if we had a situation like this, when water comes along for this guy, okay, we've got these ions here. These are going to be more strongly attracted to one another than the water. And that, therefore, silver chloride is not soluble in water because they are held together too tightly. So the attraction for these is greater than the attraction over here. And you typically a lot of times see that in your heavier metals, like lead is very common for that to happen with. What else? There's other ones too. And then for a lot of your polyatomic ions, like your chromates, they're typically going to be insoluble. So you'll see that a lot of times for those. Cobalt is typically one that's insoluble. So you'll see that sulfate is common too for being insoluble. And you can kind of go back and see, like if you go back to this chart that we gave you, if you were able to keep that, PO4, 3-, that was another one. Okay. You can always, obviously not on a test, but when you're working on homework, you can always look up substances too to kind of verify your hunches. You should start to try to get kind of in a rhythm of being able to kind of feel out and see, like say to yourself, oh, I think that's insoluble, and then go back and double check it. Okay. So like I said, when these ionic solids are put into water, they're going to fall apart and they're going to get surrounded by the water molecules. And we talked about this the other day. And we talked about situations where if you ran out of ions first and you still had water left over, that would be called an unsaturated solution. And then there's other situations where you're going to have all of your water will be occupied. Okay, you'll have ions here where the water's surrounding ions, and all of that's occupied, and you've got extra ions left over. And then that's going to be saturated, and you're going to end up with extras on the bottom. Okay. So those are called ion dipole interactions, is the attraction between the dipole of the water and then the ion that's now separated. Water can also dissolve non-ionic substances as well. So you can see here that with acetic acid, that's not, that it'll surround that acetate ion. And the attraction allows it to dissolve in the water. Not all substances can dissolve in water. Don't use like dissolves like. We don't like that. You can use it in your brain, but don't actually write it on paper. Okay. So the intermolecular forces that are present will allow it to dissolve because they are, they're able to interact. So like I was saying with like your water molecules, when you have your water molecules, with, oh gosh, this is really acting up today, guys. So when you have your, when you have your water molecules, those water molecules are attracted to other water molecules. And if you have, I'm just leaving it. If you have a nonpolar substance come nearby, it's not going to be able to break in and interact like this does with the water molecules. The water molecules are going to stay together and not allow the nonpolar substance in there to be able to get dissolved. So that's why oil and water don't mix. It's because of polarity. Now, your elementary, middle school teachers would always tell you density. No, density, the oil is on top. Okay, that's why. But the reason why they don't mix is because of polarity. It's not because of density. But a lot of them don't know what polarity is. So you get those answers. And that's okay. I mean, there's a lot about chemistry that I don't know that you guys are going to go on to college and go, yep, Lippy lied to us. So, and it's not because I'm lying. It's because I don't know.
Why does acetic acid dissolve you?
It's still polar. It's still polar. It's just not ionic. All right. So there's 3 steps that have to occur. The solute particles have to separate. So that's where I was talking about the NaCl. They have to separate from one another, and that takes energy. So you can imagine it kind of like if you had 2 magnets and you had to pull them apart, you'd have to put energy in to that. And then the solvent particles, your water, has to separate from other water molecules. So that has to separate. Again, think of 2 different magnets that you're pulling apart. And then these guys, your water and your chlorine, or your water and your sodium, have to come together and establish. Okay, and that's kind of like the magnets popping back together. It doesn't really take any energy on your part. It just kind of happens. And that's where energy is released. So energy added, energy released. When energy is required, what do we call that? Endothermic, yep. So this is an endothermic process. This is an endothermic process. And this is an exothermic process. So when we were talking about like the hydrochloric acid and diluting that down the other day, when we are diluting this down, your hydrogen and your chlorine has to come apart. Your waters have to come apart. And then when these guys come back together and get, brought back together, where your hydrogen would actually be attracted to the oxygen here, we said that there was a lot of energy. We said that it was highly exothermic. Remember that? Gave off a lot of energy. And I said, like, for sulfuric acid, I actually do it in an ice bath because it's so exothermic. What that means is that there's not a lot of energy that's needed to be input. But when we get to this step, there's a huge amount of energy that's being given off. So again, the energy needed for each step depends on the IMFs of the materials. The stronger the IMFs, the more energy is involved. Polar substances will dissolve into polar solvents, and nonpolar will dissolve in nonpolar. Nonpolar substances don't dissolve in polar, and polar substances don't dissolve into nonpolar, because there's not enough energy released in the last step to negate the energy needed for these steps. They can't pull them apart. They can't pull the different things apart so that they're not able to get to this step. So when two substances can't mix, they're called miscible. And when two substances when they can mix, they're miscible. And when they can't, they're called immiscible. And this applies to liquids. So when they say miscible or immiscible, they're talking about two liquids being mixed together. Questions? Okay. So I do. What type of IMFs? What type of interactions here? Okay. So will they dissolve? Will this dissolve better in a hexane, or will it dissolve better in water? So what type of IMFs are in NaCl?
LDF.
Okay. Everything has LDF. So this one's just LDF here. This one is, what is water? Gonna be mean to me all day. Seriously. Okay. All right. It is LDF, but overriding the LDF, you're going to have the ion interaction, right? Because they're ionic. Ionic, yep. All right. What is this guy here?
No.
LDF, yep. What is this guy?
LDF.
LDF only, yep. Because it doesn't have, if you draw it out, it's double bonded to your oxygens here. And your carbon, there's nothing on that. So it's just LDF. And then what about this guy?
LDF, dipole, dipole.
Yep, LDF and dipole. Okay, so will this, is it soluble in hexane or in water? Which one? In the water, yep, good. What about this guy? Hexane. What about this guy? Hexane. And that's better. It does dissolve in water. I mean, you have pop, okay? But that's asking which it will dissolve better in. And then what about this guy? Okay.
So is it just the more like the stronger the IMFs? Like yeah.
Yeah.
Wouldn't CH2O have 8 bonding as well? There's no hydrogen. Oh, okay, makes sense.
Yeah, I think that's the structure of it. I'd have to. Okay. Yeah, there's no hydrogen on that oxygen, so it's not hogging, but it's going to have dipole bipole. All right. Draw a molecular level diagram that shows what's happening in this reaction, and then be sure to show the solution before and after the reaction takes place and include a key.
Oh.
Some good coffee this morning.